To associate the concept of a spinning toroid's angular momentum with the fall in orbital circumstances, we delve into the physics of orbital motion and centripetal acceleration, both of which involve a constant falling towards the center of gravity while maintaining angular momentum. The orbital fall. In orbital mechanics, objects are in free fall due to gravity, but they remain in orbit because their tangential velocity provides enough angular momentum to continuously miss the surface of the planet. 1. Balance between gravity and angular momentum. Gravity pulls the object toward the center of the planet, causing a constant fall. Angular momentum L equal I omega ensures the object stays in a stable orbit by providing a tangential velocity. The condition for orbital motion is frac gm r2 equals frac v2 r, where g is the gravitational constant, m is the mass of the planet, r is the radius of the orbit, v is the orbital velocity. 2. Angular momentum in orbit. Angular momentum plays a key role in orbital motion as it's conserved. For a given mass m in orbit, L equals mrv. If L is insufficient for the gravitational force, the object will fall toward the planet instead of maintaining orbit. The spinning toroid and the orbital fall. Now, consider a spinning toroid with angular momentum, L equals I omega. 1. Can it mimic orbital behavior? For the toroid to stay aloft, mimicking an orbit, it must balance the gravitational pull with either tangential velocity. If the toroid spins fast enough to convert angular momentum into a form of dynamic lift or thrust, it could hypothetically fall like an orbiting object. Gyroscopic effects. Leveraging angular momentum to counteract gravitational torque can stabilize the system, but requires additional mechanisms to provide lift or simulate free fall. 2. Why the orbital fall is different. In true orbit, the fall is balanced by tangential velocity. For the toroid, spinning alone cannot achieve this balance. A spinning object does not inherently generate horizontal motion. It only stabilizes its orientation due to gyroscopic effects. Unless additional forces, e.g. propulsion, are applied, the toroid will not enter the continuous freefall characteristic of orbital motion. Connection to orbital circumstances. A spinning toroid can simulate aspects of orbital dynamics if 1. Angular momentum provides stability. A spinning toroid with sufficient angular momentum can stabilize itself against external forces, similar to how angular momentum stabilizes satellites. 2. Lift or thrust offsets gravity. To stay aloft, the toroid must create sufficient thrust or lift to balance gravitational acceleration, analogous to how tangential velocity offsets gravity in orbit.